For this section of questions, we're going to look at 9 through 12, and the instructions are all the same for these questions. If you look at your review, you'll see it's giving you three numbers. It's telling you that these numbers represent the lengths of the sides of a triangle, and it's asking you to use the converse of the Pythagorean theorem to decide whether this triangle formed by these lengths would be a right triangle, an acute triangle, or an obtuse triangle. So in each of these scenarios, we're going to basically do the same thing. We're going to plug these numbers into Pythagorean theorem and see if it actually makes Pythagorean theorem true. So in order to do that, the first thing you're going to have to do is identify which one of these, if this is a right triangle, which one of these would be the hypotenuse. And so that will always be the largest one. So right away we see that 15 is definitely going to be our hypotenuse. I put that in quotations because we technically don't know if this is a right triangle yet or not, but that's the one that we want to focus on. So Pythagorean theorem, you remember, is leg 1 squared plus leg 2 squared equals hypotenuse squared. So 8 and 12 are going to be our legs, and 15 is going to be our hypotenuse. So we're going to do 8 squared plus 12 squared, and we need to compare that to 15 squared. So I'm just going to put a question mark in between there for now because we don't know if it's equal yet. We don't know if one side is greater than or less than. So we need to check and see. All right, so 8 squared is 64, 12 squared is 144, 15 squared is 225. Then we'll add these parts together, so 64 plus 144. You can use a calculator for that if you need to, just to get a quick answer. That comes out to be 208. And so here we see that the side of the 15 squared is actually larger than the side of the 8 squared plus 12 squared. So what we say here is that clearly we can see that it's not a right triangle. These two numbers did not work out to be equal. So now we have to answer the question, is this an acute triangle or is this an obtuse triangle? And in class we talked about how you can visualize this, you can think about this. So the side that was supposed to be the hypotenuse ended up being too big for the two legs. So if you imagine this as your two legs, and you'll just have to fill in an imaginary hypotenuse here with your mind. If it was a right triangle perfectly, then this length squared would be perfectly equal to this length squared plus this length squared. But the hypotenuse side is a little bit too big. So imagine this hypotenuse side being bigger than it is right now. In order for this side to be bigger, we would have to push these two sides apart. And what that does to the 90-degree angle is it expands it out to be an obtuse angle. So anytime the side that's supposed to be the hypotenuse, anytime that side is bigger than the other side, this is going to be an obtuse triangle. All right, let's move on to the next one. All right, so this one's a little bit trickier because there's a square root value in there. So remember from last example, the first thing you need to do is decide which one of these is going to be the biggest side so that we can tell which one's supposed to be the hypotenuse, right? So it's easy to tell the difference between 5 and 3, but square root of 39 you actually have to think about. What number would the square root of 39 be approximately so that we can compare it to the other two numbers? So there's a couple different ways to do this. Obviously, you know, at home you can type this into your calculator and see what the value is. But on the test, I'm not going to let you use a calculator for these questions. So instead, you should think, you know, what's a number that's close? Well, there's a couple different ways you can do this. So one way is to think, what's the closest number to 39, below 39, that you can think of that would be easy to square root? So in my mind, that brings me to square root of 36. I know that the square root of 36 is 6. And so the square root of 39, since 39 is just a little bit bigger than 36, the square root of 39 should be a little bit more than 6. That helps me to know that the square root of 39 is the largest of the three numbers here. Another way to think of this, if you wanted to, would be to think, well, what would 5 look like if it was written as a square root. So for instance, I know that the square root of 25 is the same as 5. And if I thought that same way for the 3, what number could be square rooted to create a 3? That number would be 9. So actually I can compare the numbers this way too. Clearly the square root of 39 should be bigger than the square root of 9. Excuse me. And the square root of 39 should also be bigger than the square root of 25. So that's a couple different ways that you can use to compare numbers that are not in the square root to numbers that are in the square root. All right, so this one comes out as being the largest value. That one has to be our quote-unquote hypotenuse. All right, which means these two are our legs. So drop these two into Pythagorean theorem as the two legs, 5 squared plus 3 squared. And that would be, well, we don't know if it's going to be equal, but how does that compare to the square root of 39 squared? So on this side, we would get 25 plus 9. 25 plus 9 would be 34. How does that compare to the other side? Now, if you've forgotten your square root stuff, this may be a little bit confusing, but hopefully you remember that the square root operation is the inverse of squaring. So whenever a square root gets squared, they actually just cancel each other out. So the square root of 39 squared comes out to just be 39. So we can see that the hypotenuse side, once again, is the bigger side, and the legs are too small to match it. So that's just like the last problem, and that is an obtuse triangle. Let's move on to the next question. All right, no square roots here, so it's easy to tell that 30 is the potential hypotenuse. So we can drop this straight into Pythagorean theorem. 24 and 18 will be our legs. So used to writing Pythagorean theorem that I can't stop myself from writing an equal sign. All right. Is 24 squared plus 18 squared actually equal to 30 squared? So let's find out. 24 squared is 576. 18 squared is 324. Is that equal to 30 squared? 30 squared would be 900. Go ahead and add these two together, and you will see that it comes out to be 900. So in this case, we see that the side that has the legs is exactly equal to the side that has the hypotenuse. So this does actually make Pythagorean theorem work, and that means this is a right triangle. This is probably one of the easier examples because when it does become equal, when the two sides become equal, it's automatically a right triangle. All right, let's finish up the last one in this section. So this one is probably the most difficult one just because of the form of the side lengths. Every single one of them involves a square root, and some of them have numbers outside the root, some of them don't. So it's kind of hard to compare, Is 3 square root of 2 bigger than or less than 2 times the square root of 10, And how do those compare to the square root of 22? So I'll start by showing you the way to do this without a calculator. If that doesn't really make sense or whatever, I will let you use a calculator for number 12. But let me start by showing you the analytical way, no calculator. So 3 times the square root of 2 can actually be written in a way where all the numbers are inside the square root instead of having anything on the outside. So I want to remind you that numbers that are inside the square root can come outside of the square root if it's a perfect square. And so, for instance, this 3 is on the outside of the square root, but we can put that 3 back inside the square root if we just think about what number would have to be on the inside of the square root to create a 3 on the outside of the square root. Another way of asking that is, what number would have to be inside the square root so that the result would be a 3? So most people will be able to come up with that pretty quickly. It's the number 9. So in order to put this 3 back inside the square root, we have to think, oh, it must have been a 9 inside the square root before it came out to be a 3. So what that means is that we can put that 3 back inside by making it become a 9. Now there was already a 2 there. When we put that 9 back in, it has to be multiplying that 2, because we've learned in class that the only way you can simplify square roots is if the operation is either multiplication or division. So when we put that 3 back in there and make it become a 9, it has to be multiplying. So 3 square root of 2 is actually the same as the square root of 18. All right. Now we can do that same process for the second one as well. The 2 had to be some number inside the square root before it came out. So all we have to do is think, what number would have had to be under the square root in order to create a 2 on the outside of the square root. And I think most people would be able to come up with that. It would be the number 4. So if we want to put that 2 back inside the square root, we can put it back inside as a 4. The 10 that's already there would have to multiply then by that 4, and that would give us the square root of 40. So now we've translated everything into a value where all the parts are inside the square root. Now it's very easy to compare. So we can see that square root of 40 is actually the largest number. All right, so this one is going to be our potential hypotenuse. Now, if you didn't understand that or just not quite sure about what I'm saying about putting the outside numbers back into the square root, worst case scenario, you can go to your calculator and you can just type in 3 times the square root of 2 and get a decimal value for it. All right, so do that if you need to. But we know that this one is our hypotenuse. We're going to choose these to be our legs. So 3 square root of 2 squared plus our other leg, square root of 22 squared, is that equal to the value of 2 times the square root of 10 squared. So square root of 22 squared, remember that the square root and the squared cancel each other out, so that actually just comes out to be 22. Here you might be a little confused for a moment, but it's actually quite easy. You can look at the 2 pieces as, they're multiplied, but you can think of them separately. So you can think, okay, both of these 2 pieces need to be raised to the second power. So 3 has to be squared. That would be 9. And the square root of 2 has to be squared. And that would be 2. So this would actually just come out to be 18. And we can use that same thought process to figure out what 2 square root of 10 would have to be. So again, 2, you can think of what is 2 squared. That would be 4. And then what is square root of 10 squared? And that would be 10. So we get 40 on that side. So now 18 plus 22 makes 40. We already had a 40 on that side. And we see that once again, this comes out to be equal. So hey, this has got to be a right triangle. Right, as we solve these 4 problems, 9 through 12, you'll notice none of them came out to be an acute triangle. Sometimes that's just how it works. But I want to remind you that if these 2 sides do not come out to be equal, all you have to do is look at which side is the larger side. So in the first 2 examples we did, numbers 9 and 10, the hypotenuse side was the side that came out to be larger, and that's what made it an obtuse triangle. If you if you encounter an example where the leg side is the one that comes out to be larger, then that would be the acute triangle. So just because we didn't do an example with acute triangles doesn't mean you shouldn't be prepared for it. All right, that concludes this section, and we'll move on to the next section in another video.